Hello everyone and welcome back to this next lecture in the DC to DC converter series. It has been a while and I was mainly busy with recording my next online course which is now available online. So as before I start this lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses on the MOOC website Udemy. So this is my latest course, which is what I was working on for the past month or so. The title of this course is Control Analysis with Python for Grid Connected Converters, and in this I talk about how we can design controllers using Python. So this requires some basics of Python already and also some requirements that you must know how to simulate with Python Power Electronics. I start off with the basic grid, talking about some grid computations like frequency estimation, and then I go into some basics of control systems, right? Basics of control systems without any real engineering relevance, and then gradually I start off with system analysis, about describing transfer functions using Laplace transform, frequency domain representation, and also analysis of systems using Bode plots, which is a frequency response characteristics. Finally, I describe the Python control package which can be used to both analyze as well as design controllers using frequency response characteristics. I talk about a few controllers such as proportional controller and PI controller in the stationary reference frame, and then I move on to synchronous transformations where I talk about the synchronously rotating transfer reference frame where we can then design a PI controller in this particular reference frame. And finally, there is a simulation of a power converter, that is a single phase converter, edge bridge converter connected to a single phase grid where we control the current that is being injected by the converter to the grid using PI controller. So this course is brand new. It has almost 33 hours and it talks about mostly control and how you can analyze and design control systems using Python and mainly the Python control package. This is not a hardcore power electronic course. It is mainly an introduction to controls for power engineers using free and open source software such as Python. So by all means check it out. This is my latest course, and of course if you need other courses, there are other courses such as this one, simulating power electronic circuits. Just scroll up, simulating power electronic circuits using Python, and in this I talk about the basics of how you can simulate circuits using Python and Python power electronics. There is some very basic theory about power electronics, and finally there is a case study of how to simulate a buck converter. If you're interested more on the digital signal processing side, there is another course which is basics of digital signal processing for power engineers, and in this I talk about how you can design filters using Python. So I talk about the basics of signal processing, basics of Laplace transform, frequency domain representation, and finally there is a case study of how to design a low pass filter and a notch filter using the signal package in SciPy. And another course which I have is on simulation of magnetics for power electronics using Python, and in this course I talk about how you can simulate magnetic components such as inductors and transformers for power electronic application, and there is a case study of how you can simulate a flyback converter. So these are some courses which I do have on the MOOC website Udemy. The links for these courses are provided in the description for this video, so if you are interested, please do check them out. We need to do a little bit of recap because it has been a while. So this is where we had left off in the previous lecture, where we had finished editing the parameters of all our circuits. So for example, if we go back to our circuit list, we have the usual voltage source, which is connected now instead to a 2-winding transformer, it is now connected to a 3-winding transformer. So for example, we have the usual windings, which are basically the windings which supply the load, but now there is a tertiary winding whose job is now to supply this energy stored in the magnetic field of the transformer back to the DC supply when the switch is turned off. So we had already gone through this and we can go through this again when we actually simulate the circuit. But for now, this transformer, let's go on to the next one. this transformer, well, actually the name has to change. It is no longer a 2-winding transformer, it is a 3-winding transformer. So for example, the main 2 windings are the one winding which is connected to the DC supply, and this is connected to the DC supply through the switch S1, and the secondary is feeding the load, of course through a filter. We have an LC filter, just like a buck filter. The third winding, this is the winding whose sole purpose is to transfer the energy stored in the magnetic field of the transformer back to the DC supply when the switch is turned off. Because remember, the magnetic field in the transformer must never be broken. So for example, the magnetizing current must continue to flow. Because remember, the magnetic energy cannot just dissipate. That's not something you want to happen. So with this, let's go on to the next circuit. The next circuit is of course the secondary load. This is the secondary of the transformer which is connected to the load. However, we have broken this circuit to include a filter. So for example, the load is connected to the secondary through a filter, and that filter is this one. It's similar to a buck filter where we just have a diode, an inductor, a capacitor. Right? So the diode is to make sure that current flows only during one particular cycle, that is when the switch is turned on, and when the switch is turned off, there is no current flowing through to the secondary, or rather to the load. So these are our circuits, and if you have a doubt, I would say please go back and just review any of the previous lectures. So with this, the next step is we now have to change our transformer. Since we've edited the parameters of all our circuits, the one change which I would make is I would rename this particular circuit. So let me go back and let me do that change. Let me rename this here to 3-winding transformer, because that is what it is now. And this is a 3-winding transformer. So of course, let us go back to the main page and let's go and make that change. Now what is important here is we should export the parameters just in case, because I do realize I may have edited it. So let's go back here. Oh, I see. I've already made that change. That is a problem. Let me go and reverse this change once. Because it is now complaining that it doesn't see that. See, this is not a good idea. All I have to do is change one word. So all I'm trying to do is export the parameters so that we have the latest parameters, because we did make some changes. We changed all the polarities of our windings, especially the winding 3. Because this winding 3 is a freewheeling winding where we are going to use this to transfer the energy stored in the transformer back to the DC supply. So therefore, I will export it. And with this export, we should be good to go. We now have the latest parameters. So now I can go and make that change. So let me go rename it 3-winding and the parameter file as well. So with this change, let me go back here to my main page, go to the add circuit file, and I will remove this circuit 2-winding transformer. And we will replace it with a 3-winding transformer. So let me go back to my documents, energy series, simulations, forward converter, and here we have the 3-winding transformer. So I will just call this 3-winding transformer. Save it, and always when you make a change, in this case a major change because we have changed a circuit, you must click on process circuit schematics. And the good news is there are no errors, and we didn't expect any because we haven't changed the circuit. But what is most important is we need to import our parameters again. because remember, it will create parameters with default values only. All of these are default values. So we do need to upload our previous file, and that is the 3-winding transformer params.csv. So let me go and upload this. And we are good to go. These are all our parameters. So we now have an updated circuit, but at this point of time, we do need to take a slight detour, because remember, we now have this 3-winding transformer for which we do not have a model. So like for example, let me go over to my simulations, and if I go over to my flyback converter, I do have, I'm looking for the magnetic transformer model. So I need the transformer model.csv, and let me just paste it here, and let me go over to my editor and open that file. So this is the transformer model.csv. Now as you can see, this particular model, quite obviously, is written for a 2-winding transformer. This now has to be changed to a 3-winding transformer. So we cannot directly use this entire circuit or directly into a forward transformer. Whenever we are making, or rather we are building a model of a magnetic component, it is always advisable that we test it separately, in exactly the same way that we spent a few lectures in simulating a basic transformer. Now we need to spend maybe 1 or 2 lectures in simulating a 3-winding transformer, and that's what we need to do before we move on. So what I would do, I'll go back to my web browser and let me go and create a new simulation. So let me create a simulation. I will call this 3-winding transformer. And let me call this test circuit, because this is just a test circuit for the 3-winding transformer. Copy it, and here I'll make the usual changes. Since it is we eventually want to test a high frequency transformer, I will make it 1 e⁻⁻8 so that it's fast enough. Now we need to create a new directory. Let me go to my file browser, and exactly the way we had a basic transformer, I'm going to create a new one, which is 3-winding transformer. And let me go and copy my transformer windings. So I will go and copy all these files and paste it here. So these are my windings, or rather these are my files. So let me go quickly and take the directory path and paste it here and save it, and we are good to go. So let me go and add the circuits. Let me go and choose a circuit which is now in the different directory, 3-winding transformer. This is the 3-winding.csv. So I will call this 3-winding transformer. Now of course this is not enough, because this is just the transformer. We do need to create a couple of other directories. So I will just go and close all my other circuit files so that I don't get confused. And now let me open it again. So this is my transformer. So in order to test it, I need circuits connected to each winding. I need a circuit connected to winding 1, to winding 2 and winding 3, right? Now the simplest way to test it is if I connect a source to winding 1 or winding 2 or winding 3, whichever, and I connect loads to winding 3 and winding 2, right? So basically one winding is connected with the source and the other 2 windings are connected with loads. So what we need to do, let's create a new file and let's start creating the source. So let me just put some wire elements. And stretch it. Since it is a test circuit, I don't have to bother too much. Let me just pull some wires. Now what am I going to do? I'm going to put a voltage source. And this voltage source can be something like Vn. And this of course needs a resistor. I'll just put resistor Vn. And let's measure the amp current as well. So let's put an ammeter. And let's call this also Vn. And we should measure the voltage. So let's just call this voltmeter Vn. And now we can go and pick out our winding jump label. So I will just pick these two out. And let me go and paste it in the other file. Surprisingly, they came together. Never mind. So one of them is jump winding 1, transformer term 1. The other is jump winding 1, transformer term 2. So these are the two terminals of winding 1, which are now connected to this source. So let us save this file and come to energy series, simulations, no, wrong folder, simulations, wrong folder again, 3 winding transformer. Now here, most important, choose the format as CSV. So since I'm in Linux, I'm using text CSV. If you're using Windows, Microsoft Excel, you might have to choose MS-DOS CSV, right? So just delete this and make this voltage source. And it'll ask me some questions. These are all used. Field delimiter has to be a comma, should not be a semicolon, should not be a colon or a tab. Make sure it is a comma. The text delimiter can be a double quote or a single quote, doesn't matter. And we are good to go. So with this, I will just create another new file. And this will be our loads. Actually, load is better the other way. So let me just, because the load is usually being supplied. I mean, it's just a convention, but easier this way. And let me just pull this out. So what do I need? I need a resistor. Let me call this load 1 because we will have two windings with loads. So I'll call this resistor load 1. And let me give it an ammeter, also load 1. I think that's all I want. If you want, put an inductor, no problem. And here let me call this a voltmeter. And let's call this load 1. So I just have to delete these two. And let me go over to my transformer and pick out winding 2 jump labels. So this one and this one. And let me copy it into my new file. It only copied one, I'm not sure why, but anyway, let me paste it here and let me paste this one here. So I will need to change one of them. Let me just expand this to know what they are. So they are both terminal 2. All I have to do, for some reason it has picked out the wrong one. Yeah, because it is winding 2. There's probably a bug in my spreadsheet software, but anyway. So I will need to change both of them. Winding 2, term 1, and winding 2. This can remain term 2. So this is now the load connected to term winding 2 of the transformer. So I'll save it again. Energy series. And let us click this to text CSV. So I will call this load 1. Usual questions, just say OK because their default values are good enough. And one last one. Actually, I don't have to create a new one. Let me just save it. Save as, and I will call this load 2 because I don't have to make any changes. All I have to do is just change Actually, simpler thing to do is just change winding 3. Winding 3, these can be load 2 and load 1. So I can just take this entire thing and do a search replace. So I just have to say load 1 is to be replaced with load 2. So I'll just say find, replace, 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 close, we are good to go, right? So usually almost all spreadsheet softwares have this select and find replace, which makes life a little easier. So now we have load 1 and load 2. So let's go add this to our simulation. So we have load 1. I will call this, actually we should start with the source, not the load. So we should say voltage source so this is voltage source, save it, choose another one, load 1, call this load 1, save it, choose load 2, and we can save it as well. So we process the circuit schematic, and we do not have any detectable errors. So with this, we now have a test circuit for our 3-winding transformer, and with which we can now write our new magnetic model, and we can now adjust this magnetic model to account for the 3rd winding in our transformer. So we can then take this transformer model and place it in a forward converter, which is what we were working on before. So since this lecture is getting pretty long, I'm going to stop this lecture now. If you have any doubts about what I did or why I'm doing what I'm doing, please do post either in the comments or send me an email or message me on social media. Otherwise, I will see you in the next week, where we will continue with simulating this test circuit for the 3-winding transformer. So thank you so much and see you soon. Goodbye for now.